In this video, we will focus on the classical approach and probability, where we can count up the number of events that we're looking for and divide it by the total number of events or possible outcomes. So the simplest of all probability examples is just the flipping of a coin. Now, some will argue that, well, it could land on its side, but the probability of that happening is so small that we could consider it negligible. So we assume that the probability of either a heads or a tails is 1/2 because there are two sides and it can only happen one of two ways. What if there were more possible outcomes? So what's the probability of pulling at random the ace of spades out of a deck of 52 cards? Well, it's 1 out of 52. Why? Because there's only one ace of spades and there are 52 cards in a regular deck. What's the probability of drawing any ace out of a deck of 52 cards? Well, now the number of events we're looking for is 4 possible events. So any of the 4 aces divided by the total number of cards would be 4 over 52, and we can simplify that to 1 out of 13. And it's a good idea to leave these as a fraction rather than reducing them to an irrational number that has many digits after the decimal. What's the probability of drawing a marble out of a bag containing two red marbles and 5 blue marbles? Well, if our event that we're looking for is 2, then we divide by the total number of marbles in the bag, which is 5 plus 2, so 2 over 7. I hope that this is sounding kind of relatively simple, because we're going to add some complication here in a moment. So counting sounds easy, but it's not going to be very easy for this class, and I want to start with some basic terms. We talk about experiments. An experiment is any activity or measurement that results in an outcome. Sample space is all possible outcomes in that experiment. In the classical approach, we can count those possible outcomes. In a relative approach, sometimes we can't count those total outcomes, so we just have to measure based on history. An event is that event that we're looking for, and you can see the notation there that it's n, signifying the number of things, E standing for an event, and n is the subspace of that sample space. So one or more possible outcomes of an experience, and it is a subspace, or it is an event that could happen within the sample space. Probability, once again coming back to our simple equation, is the number of things we're looking for, n of E sub n divided by the total number of things that could happen, which is our sample space, n of E. So how many different ways are there to, or what is the probability of pulling a king out of a deck of playing cards? There are 4 kings in a deck of playing cards, so 4 divided by 52 is 1 out of 13 again. We could say that it's 7.7%. However, that is rounding, because it's not exactly 7.7%. All right, mutually exclusive events. Mutually exclusive events are events that are said to occur in isolation from one another. So my example that I have there in the box on the right is I cannot wear my pajama pants and my party pants at the same time. So I would say that the probability that I wear my pajama pants to class one day is a mutually exclusive event from the probability that I wear my party pants to class one day. However, in a subjective approach, the probability of both of those is almost nothing, so I'd say that it is negligible. But that's mutually exclusive. When we have 2 mutually exclusive events, then the addition rule applies. If we want to know the probability that I wear either my party pants or my pajama pants, they are mutually exclusive, I can add those two probabilities together to come up with the probability that I have either or. So in this example, consider that there's a set of numbers S, and it goes from -4, and you can see the number scale up to 10. Let the events E1, E2, and E3 be defined as choosing a negative number or an odd number, choosing a negative number from S, or choosing an odd number from S. So you can see that in this sample space, choosing a negative number and choosing an odd number are mutually exclusive, because the only odd numbers that I have are positive. So if I choose a number and it's odd, I know that it's not negative, and the only negative numbers that I have are not odd. So if I wanted to know the number of ways that I could choose an odd number or a negative number, these mutually exclusive events would tell me that there are 7 different ways that I could choose between those. So I could take this a step further and say, okay, what is the probability of either an odd or a negative? And that would be n en divided by n sub e. So in this case we have 2 odds, or 2 negatives, excuse me, and 1, 2, 3, 4, 5 odds, and we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So we would say the probability of E sub n would be 7 out of 10. All right, mutually exclusive events. Now this is fundamentally different from independent events. Independent events could happen at the same time. For example, I can wear my pajamas and my blue suede shoes at the same time. Therefore, these events are independent. When events are independent, we use the multiplication rule if we want to know the probability of those 2 events occurring simultaneously. So I've put a visualization here that shows that I have in my closet 2 different shirts, and I have also 4 pairs of pants. And if I wanted to look at all the possible combinations, so the probability of, for example, wearing my white shirt and my Daisy Dukes at the same time, that's one possible combination. To get the total number of combinations, I would look at the multiplication of the number of shirts I have times the number of pants. So there are 8 possible unique combinations in these 2 sets. So the probability of this event happening, of wearing my white shirt and my Daisy Dukes, would be 1 out of 8, because there are 8 total possible combinations. Now let's take a look at a coin toss. Coin tosses are independent events. If I toss a coin and get heads, and I toss it again, the fact that I got heads on the first toss has absolutely no effect on the probability that I'll get heads or tails on the second toss. Now this is common with couples that have children, that they think if they've had 4 boys in a row that there is a higher probability that the 5th one will be a girl. But this is not true. Every single one of those children have the same probability of being either a male or a female. So if these 2 events are independent, then E1, the toss of the first coin, there are 2 possible outcomes. E2, the toss of the second coin, there's also 2 possible outcomes. And for example, I wanted to know what is the probability that I would get heads twice in a row. Well, there is only one possibility that I would get heads twice in a row. But given that there are 2 possible outcomes in the first toss and 2 possible outcomes in the second toss, the probability of a heads and a heads would be 1 divided by 2 times 2, or 1 out of 4.